Welcome, ladies and gentlemen. May I have your attention, please? Thank you. Raise your hand if you did not get a red mark for today. Let's go ahead and take a look at our indefinite versus definite integrals today. We know that we can evaluate a definite integral exactly and algebraically using an indefinite integral in accordance with the fundamental theorem of calculus. If we can just find an antiderivative function for that integrand function, in this case, 1 over p squared plus 1, if we can just find an antiderivative function for that, evaluate it at my upper limit, evaluate it at my lower limit, and subtract the two, then I can do it exactly and algebraically without the use of a calculator. We can always check with Math 9 using our tech tip, right, to make sure that we've done it correctly. So I want you to be thinking, what's an antiderivative function for 1 over p squared plus 1? Right? What's an antiderivative function for that? Tess?
Inverse.
Absolutely. And so we know that this will be given by the inverse tangent of p evaluated from 1 to root 3. And so now we'll go ahead and substitute in my upper limit into my antiderivative function. So this would become the inverse tangent of root 3 minus the inverse tangent of 1, right? And we can do this exactly now using our knowledge of the unit circle. And so the inverse tangent of root 3 is an angle question. It's asking me what angle has a value of tangent that is root 3. And so I have to think in terms of my unit circle. I know that tangent comes from sine over cosine. So I'm looking for the sine over cosine ratio that reduces to root 3. So that must have come from root 3 over 2 over 1/2. So the sine must be the root 3 over 2. Where does that happen? That happens at pi over 3, right? A 60-degree angle in radians would be pi over 3. So I'm going pi over 3 for this first part. Minus, and then the second one's easier. What angle has a value of tangent that is 1? Well, that's 45 degrees would correspond to pi over 4 radians. So it looks like pi over 3 minus pi over 4. And we're still going exactly. So we're doing a pretty good job. I know that pi over 3 minus pi over 4 looks like pi over 12, because this would be 4 pi over 12s, and this would be 3 pi over 12s, so that would be 1 pi over 12. So I'm thinking pi over 12 would be exact and algebraic. So who got this equivalent? Did I make it to the end? Yes! That's great work, you guys. Awesome. So we can evaluate a definite integral using an indefinite integral. An antiderivative, that's the fundamental theorem of calculus. Nice job. Let's take a look at number 2. In number 2, we could do the same exact thing. We could find an antiderivative function for my integrand sine of x, right? I know that an antiderivative for sine of x would be opposite of cosine of x, right? Evaluate my upper, evaluate my lower, subtract the 2. But I also know that the lower limit, right, that lower limit, negative 2 pi over 3, is the exact opposite of my upper limit, positive 2 pi over 3. In last class, when we developed the definite integral properties, we saw that if my integrand function was an odd function, then integrating from negative a to positive a, right? Whatever positive area contribution resulted from area above the x-axis would be canceled out by an equal and opposite negative contribution from any area bounded between the curve and the x-axis below, right, the x-axis. And so the result in this is going to be what? 0, and we can verify that, right, doing it the long way, finding if we didn't recognize that, that's okay. If we didn't recognize that sine of x was odd, right, or that we were integrating from negative 2 pi over 3 to the opposite, positive 2 pi over 3, right? If we didn't recognize that, we could have done it the long way. Negative cosine evaluated at the upper, right, 2 pi over 3 would be negative 1/2, and then times the negative is positive 1/2, and then evaluate at negative 2 pi over 3, that would be down here, minus negative opposite of that is 1/2, which gets me back to 0. So either way, we get 0. Awesome. Okay, so what questions do you guys have about number 2? Much quicker to recognize it's an odd function. Okay, let's take a look at number 3. Ooh, an even function. And again, we've got that limits, the opposite, right? The opposite, 2 and negative 2 are my limits. However, it might be helpful to rewrite this, right, as a lower limit my lower limit with the lesser value. And so what I'm going to do is I'm going to go ahead and rewrite this using my properties of definite integrals. I'm going to say that the integral from 2 to negative 2 is the opposite of the integral from negative 2 to positive 2 of my original integrand function. So once again, I'm going to purposely flip the limits so that my lower limit is in fact less than my upper limit. Now, do we have to do that? No, but it's going to help with my subsequent evaluation and consideration, because now look, a negative times a negative overall is a positive. So now I can use my knowledge here, negative 2 to 2 of x to the 4th dx. And one more property I'm going to apply. Notice how my limits are exact opposites. Notice how that negative 2, right, and positive 2 are exact opposites. And I have an even power function. So again, I'm going to use my properties to make my life easier. If I'm doing this exactly and algebraically, I'm going to go ahead and rewrite my limits now. Instead of doing negative 2 to positive 2 of my antiderivative function, I'm going to double the integral from 0 to 2. So I'm going to do one more rewrite here. This will be equivalent to 2 times the integral from 0 to 2, just because that will result in an easier evaluation. All right, let's go ahead and find an antiderivative for my integrand function x to the 4th. I know that my constant multiplier 2 is going to stay out front, and an antiderivative for x to the 4th would be x to the 5th over 5. I'll now evaluate for my limits and subtract. It looks like x to the 5th when x is 2 is 32, right? 32. And 2 times 32 is 64 fifths minus 0. And now we see why we did that. My lower limit of 0, it makes this easy to evaluate. So it looks like I get 64 fifths. Raise your hand if you already had 64 fifths. Already have 64 fifths? Nice job. Meg?
If you didn't do the first step where you make it the opposite of negative 2 to 2,
Yep.
do you ever set 0 to negative 2?
Oh, that's a great question. No, we saw that an even function had left-right bilateral symmetry, either to the right side or the left side of the y-axis produced the same contribution, and so you certainly could have doubled 0 to negative 2 as well. We just have more negative signs floating around, and so you'd have to be more careful with your negative signs, both in your antiderivative function and in your evaluations. But no, absolutely, the property still holds true. Good question. Other questions about 3? All right, let's finish it up. So number 4, we weren't given any integrand function. Right? I mean, we were given an integrand function, g of m, but we didn't know its equation symbolically. Instead, we were told the value of the definite integral at several different domain bounds. And so it looks like we want to find the integral of g with respect to m from negative 2 to 3 if the integral from 3 to 7 is 2 and the integral from negative 2 to 7 is 8. And so I think it's helpful to look at this geometrically. So if we had some function, g, and we know that the integral from negative 2 up until 8 was, I'm sorry, negative 2 up until 7, you're about to tell me? Was 8, and we knew that the integral from 3 to 7, so just this portion right here, just this portion was 2. So if we had the whole polka dot blue was 8, and just the red portion is 2, then what must be that remaining piece? The 2, negative 2 to 3, what must that piece be? Well, that would have to be 6. Did you guys get 6? Awesome. And so that remaining piece must be 6. Raise your hand if you already had 6 then for number 4. Awesome, you guys. Way to go. What questions do you have about today's Bellwork? So a combination of utilizing our properties could result in simpler evaluations, right? But if you didn't recognize that, it still was a good practice in terms of applying the fundamental theorem of calculus. Let's go ahead then and give yourself credit for your homework assignment, OTL number 8. Give yourself credit for those that you completed, please, out of 27. Out of 27. If you have multiple pages, if you could kindly staple them together. Otherwise, make sure that your name, first and last, 2A and number 8 are clearly labeled. Your Infinite Canvas score is boxed nice and big on top, round to the nearest half point, 0 to 2. And then please pass from the back to the front. Front rowers, make sure they're facing the same direction. I appreciate your help. Okay, ladies and gentlemen, thank you for your help. I appreciate that. Today we're going to introduce an application of definite integrals. In fact, one of the main applications of definite integrals is finding area and an assortment of different kinds of problems. Today we're going to introduce the concept of finding areas between two different curves, not just between a function and the x-axis, the way that we've seen with definite integrals in the past. And so it's a big activity. In fact, we can earn up to 5 different activity stamps. So take a minute now, and if you circle your stamped eligible items, they include 1C, 3, 4D, 5C, and 7. We have a different schedule today, so 11:42, and we need a good 10 minutes for our discussion at the end, and so we want to be aiming for about 32, which gives you a little bit less than an hour. So this is a big activity, okay? Don't get hung up on the exact algebraic evaluations in the middle. I don't want you to get hung up so much on the fundamental theorem of calculus evals. I want you to focus on the concepts of setting up the definite integrals. And so I tried to make the stamps more for the setups as opposed to just for the answer numbers. I want to be looking at your integrals for the setup. Make sure that you're attentive to detail in the notation as well, in top function and bottom function, and I can see clearly in order to get those stamps in the middle. So I'm going to go ahead and pause the recording. Let's put into your groups and get going right away. And then again, we're aiming for 11:32 to come back together. Thank you, ladies and gentlemen. So our definition for the area between two curves, right, as a result of our activity, if f and g are continuous functions, and f is greater than g, right, throughout the entire interval, a to b, then the area bounded between the two curves is given by the definite integral. From the left x value a, scanning towards the rightmost x value of the region b, top curve, well, since f is greater than g throughout the entire interval, my top curve is f of x, minus my bottom curve. Since g of x is less than f of x the entire interval, then g of x will be my bottom curve with respect to x. Notice how anytime we have an integral symbol, we have to have a dx or a dy or a dl, right, depending upon what my independent variable is. If these functions, if I'm integrating with respect to x, then these functions should be solved for y equals and have x's in them. Right? This variable has to match. Just like when we went and did our u substitutions, we had to figure out how to rewrite it. So we had du here and have u's in my antiderivative function. Same is true here. If we have integration with respect to x, these must be solved for y and have x's in them. Okay, so there's in general my definition for the area between two curves. We're going to save this for next class, as well as our oil rig application, and let's focus in now on our closure. And so what we're going to do is we're going to think about two different ways in which we could express the area in between these two curves. And so first we're going to do it the way top curve minus bottom curve, okay, top curve minus bottom curve. And then the second way we're going to do it is using Ella's method, right? Scanning the region from bottom to top and doing right curve minus left curve to preserve, to make sure that the rectangle heights are positive. All right, so let's go ahead and I'm going to clone this first so that we have it both ways. Okay. So first, let's go ahead and consider my region. And let's suppose that we're going to scan this region from leftmost x value to rightmost x value. That would ensure then that my delta x values, my widths of my rectangle are positive if I'm scanning from left to right like I read a sentence. Let's go ahead and draw in a typical rectangle. So everybody, if we were to draw in a typical rectangle, to connect the top curve to the bottom curve, the height of that rectangle would be kept positive so long as I did y equals top curves minus y equals bottom curve. And so the area in this case then would be given by scanning the region from left to right would be from A to B with respect to x. My top curve, right, would be y equals t of x for top curve. And so my top curve would be t of x minus my bottom curve would be given by b of x for bottom curve. These functions will be solved for y and have x's in them. The independent variables will be x's in them, right? For number 2, let's go ahead and look at this a different way. Let's look at this Ella's way, okay? So in Ella's way, we still have our shaded region. But now a typical rectangle, right, is going to be, well, kind of a horizontally oriented rectangle where we're scanning the region not from leftmost x value to rightmost x value, but from least y value up until greatest y value. And so now we're going to scan, for number 2, we're going to scan from bottom to top. And so my lowest y value would be what? C, up until the greatest y value of the region would be what? D. Good job, you guys. These are y values on my integral symbol now because I'm integrating with respect to y. I'm scanning from bottom to top. To keep the heights of my rectangle positive, I will do right curve, right, solve for x, minus left curve, solve for x. This will guarantee that my heights are positive, right? No matter where I am in the xy coordinate plane. Right side minus left side will be a positive value. So let's draw on a typical rectangle here. And we'll keep that height of the rectangle positive by doing right curve minus left curve. So solve for x. My right curve then would be x equals r of y with y in it. R of y with y's in it. No, I didn't take French. Minus the left curve, solve for x, would be x equals L of y with y's in it. Awesome. So there's the integral from bottom of the region to top of the region. Those are y values. They must match, right, with respect to which variable. And then right curve, solve for x is x equals r of y, minus left curve, solve for x is x equals L of y. Awesome. What questions do you have about our investigation today? Jake?
So if it's the right curve when you're looking at x, it will be the left curve when you're looking at y, the direction split?
Typically, but it would depend on what your region looks like, right? Typically, yes, but not always. All right, I'm going to go ahead and save the recording then.